La exposición que clausura nuestro Congreso Futuro Aysen 2018 la presentará el doctor Noam Weisbrod y se titula Desafíos globales y regionales de seguridad hídrica y alimentaria. El doctor Weisbrod es director del Instituto Zuckerberger de la Universidad de Ben Gurion en Israel. Su investigación se centra en la hidrología de contaminantes en general y el flujo de fractura y el transporte coloidal en particular. Se ha centrado en estudios relacionados con los mecanismos que controlan el transporte de coloides, nanopartículas y facilitado por coloides en el subsuelo, bajo una variedad de condiciones ambientales. Otra dirección importante de investigación se relaciona con los procesos que ocurren dentro de las fracturas y los medios porosos heterogéneos en la zona vadosa y su relación con la evaporación, la salinización y el intercambio de gases tierra-atmósfera. Una gran parte de su investigación actual se centra en las condiciones de zona instaurada, donde los procesos en la interfaz aire, fluido, sólido juegan un papel importante. Damos la bienvenida al señor Weisbrod.
Thank you. So, first of all, I would like to thank the organizers for giving me the opportunity. I gave a presentation yesterday in Santiago and now here. It's very exciting. I was here 30 years ago as a backpacker, as a mochilero. Although a lot changed in 30 years, it's still Patagonia. So there are a lot of similarities. So I will talk a little bit about global and regional water and food security challenges. And as mentioned, I'm coming from the Zuckerberg Institute for Water Research, which is part of the Ben-Gurion University of the Negev in Israel. And under this title, I will try to cover pretty briefly a few things. First of all, we'll talk about the problem, why we have such a big problem when we talk about the food, water, sanitation, and energy nexus that they're all linked, we will see. And I will try to give some examples and highlights. And then I will try to zoom into our region. I'm coming from a region where water scarcity is something that we live with from our establishment, so we had to find some solutions, and we'll see what we found. Again, with some case studies and examples, and then I will try to summarize in a kind of a personal perspective. So first of all, it is very important to understand that water, food, and sanitation are linked. It's basically a triangle of things that are linked quite directly, and we will see why during this presentation. Now, I think that most people in this room are well aware of the fact that we're living in time where water scarcity is becoming a bigger and bigger problem. You are living in an area where there is a lot of water, so maybe you don't feel it so much, but if you fly north to the northern part of Chile, I'm sure that people will understand very well what I'm talking about. And the situation is just getting worse and worse. And without too many details, I will just mention that a recent report that was published by the United Nations last year predict that in 2050, which is just 30 years from now, 45% of the world population will be living under water scarcity. 45% of the world population, it's quite a few billions of people, so it's a big problem, and it's just getting bigger. Again, I'm coming from a part of the world where water scarcity is something that we live with from our establishment, and we had to find some solutions. Now, when people talk about dry lands, in many cases we think about rare areas, some deserts, the Kalahari, Atacama here, or the Namib Desert, you know, small sporadic things, but actually more than 40% of the world terrestrial area is defined as dry land, and 35% of the world population is living in dry lands. And this number is just going to increase and increase over the years because most of the people are moving to dry lands, or more and more population are growing in dry lands because this is where there is space for more people. Now, talking about space and more people, one of the major problems is the fact that there is a severe population growth in the last 20, 30 years, and there are quite a few models and a lot of science that is being investigated to predict the population in 20 years, 30 years, 50 years. The models predict different numbers according to some parameters, but no matter how you put it, we are in a very, very extreme population growth if you look on the time scale. And obviously, more people means more food. And more food means more water. Just to understand, to produce 1 kilogram of meat, we need between 5,000 and 20,000 liters of water. Okay? So we drink, let's say, between 2 liters and 5 liters per day, but we eat, or the amount of water that is needed to produce our food is between 2,000 and 5,000 liters per day. So most of the water is being used to produce food. And here we can already see quite clear the connection between water and food. Now, when we talk about population growth, a very important fact is that most of the population growth is in the developing countries. And the developing countries is the place where water scarcity is already a huge problem. And this is fact. I mean, you can see Africa, for example, the continent of Africa that has a population growth that is way more than any other continent in the world. Now, if we look on the overall population growth in the world, we see that it's really going after the population growth in the developing countries. But if we look on the land mass that is being used for agriculture here, we see that it follows the population growth in the developed countries. And here again, I think it's already quite clear that we have a problem. Again, a different way to see the problem, if we look on the increase in the total demand for food, cereals, meats, and roots, you see in green, most of the increase is in the developing countries, and in the developed countries, the increased demand is much, much lower. Now, this talk is not about the developing countries. It requires a different talk, but a few numbers. More than 1.5 million kids are dying every year due to water-related disease. More than 1.5 million kids every year. About 500 million school days are being lost every year due to water-related disease, and this is almost 100% in the developing countries and more. So we do have a big problem in the developing countries. And I just show a few examples of pictures that we took, the students took in some of the excursions that we're doing with our students every year to villages in Africa. And I think that you don't have to be a physician or a hydrology professor to say that if you drink this water or this water, the likelihood to be sick is really high, because we wouldn't drink such water, but they just don't have any other option. So we all know that water means life, and we cannot live without water. I think that we all know, or maybe we don't think about it, but we know that there is a very good correlation between having appropriate amount of water and in good quality to hunger, disease, and poverty. In places where there is enough water and in good quality, usually there is no hunger and poverty, and the other way around. And there are a lot of studies showing it. So I think that we can say that water quality and quantity are both essential conditions for sustainable life, and this is something that we need to remember. Now, another thing that I decided to mention, although I'm not going to elaborate on it, is the process of urbanization, which is a new game that we need to understand how to deal with, that has a very big impact on the food-water sanitation nexus. So if we look on the number of cities in 1960 and 1980 and 2011 and prediction for 2025, we see huge increase. More and more people are moving from villages, from rural areas into cities, and this is a very, very important process. We can see it here, in a study that divided toward to the developed countries, the less developed, and the least developed. It doesn't matter exactly, but we see that in all the regions, we see more and more people that are moving to the cities, even in the least developed countries, where 50 years ago, most of the population was living in villages. In 2050, half of the population will be living in cities. And this is really a new game that we need to learn how to deal with. Now, if this presentation was given, let's say, 15 years ago, and we were talking about lack of water, we were usually thinking about villages in Africa or things like that. But this is not the case anymore. And probably the best example is what we see in the last 5-6 years in the United States. There was a very severe drought in the western part of the United States, especially in California. And the people there face really big water problems. And definitely this is a very developed part of the world. So having money and not having water became a very common problem. It's not only a problem of the poor countries anymore. It's everywhere. The reasons, again, we talked about increasing population. There is a process of desertification. More and more areas are becoming dry lands. Climate change, I'm not going to get into it, and it doesn't matter if it's part of a natural cycle or a man-made process, but there is a climate change for sure, and there are more and more droughts, more and more extreme events, the seasons change, and so on. So the bottom line is that we see clear increased demand for water and food. Now, sanitation is an interesting story. Most of us are not really aware of sanitation problems, but I will just say that there is a very good correlation between areas with sanitation problems and areas with water problems. Very, very good, it's not good, but very, very clear correlation between the two. And when we're talking about bad sanitation, we're not talking about a typical flashing toilet in any Japanese hotel, if you've ever been in Japan. This is a basic way. We're talking about pit latrines. And if you have a good pit latrine, this is enough according to the UN definition. That means that you are in a good shape in terms of your sanitation system. But in many cases, these latrines have no running water nearby. The maintenance is a catastrophe. And in many cases, there is also no ventilation. So these pit latrines create a lot of source for illness and disease. Now, let's go back to water, and I already mentioned it. What is the water being used for? So every country is slightly different, but worldwide, 70 to 75% of the water is being used for agriculture. And that's a lot. So we can clearly say that water use efficiency in agriculture is a major player, or even the major player, in the global water scarcity. Or in other words, we can say that food and water securities are actually two sides of the same coin. It's actually the same thing, because without water, we cannot produce food. Now, saying that, and although if we are using efficient irrigation techniques, we can save a lot of water, and it also makes business sense, the level of adoption of efficient irrigation in the world is still very low. Even in the developed countries, we're talking about 50% or less, and the extreme cases are China and India that irrigate way more than any other country in the world, of course, because they have the highest population, and the adoption of efficient irrigation is less than 10%. Most of the irrigation is still flood or furrow irrigation. They're just flooding their fields, and that means wasting a lot of water. So I think that one of the major challenges that we're facing in this century is to feed the world in the sustainable way. And the studies show that the world food demand will almost double itself in 2050. And without increase in water productivity or significant reduction in the demand, water consumption will also double itself. And this is just impossible. So we have a big problem that we need to think about and find ways to solve. and not wait to the last moment. It's going to be too late. Now, because water is mostly being used for agriculture, we can say that our agricultural growth has to come from higher yield from the same area of land with more efficient use of water and other inputs. This is a key thing that we need to work accordingly. Now let's zoom into my region, the Middle East. This is the delta of the Nile. This is the Mediterranean Sea. This is Sinai. This is the border between Israel and Sinai. This is the Dead Sea. And again, you don't have to be an hydrology professor or a remote sensing expert to say that we are living in a dry area. And that means that in our area, the demand and the actual consumption of water is far beyond the annual rate of replenishment. And this is basically true for all the dry lands in the world, sometimes even to areas that are not defined as dry land. And what it means is that water in these regions, and if you ask me everywhere, should be treated as a scarce commodity. It's not something that can be given freely without thinking about it. And if you treat it as a scarce commodity, you start to solve the problem. But as long as you don't treat it and look at it as a scarce commodity, I think that we have a big problem and we cannot solve it. So what can we do to better manage our resources, our water? First of all, water distribution across the country. I think that in this case, Chile is the best example. South, where we are now, and north, if you could take all the water in Chile and mix it and distribute it evenly around the country, it was a different country. Obviously, it's very complicated. It's a very long country. And although I know that there are some ideas to take water from the south and deliver it to the north, it's very, very expensive. It requires a lot of energy. And so far, it's only on the table. I don't think, as far as I know, it's not being done yet. But this is something that needs to be done. Optimizing the use of natural resources in terms of quality and quantity. And I want to emphasize quality and quantity because in many cases, especially in the developed world, where we have a lot of agriculture, a lot of usage of fertilizers and pesticides and a lot of industry, the problem is not necessarily the quantity of water, the problem is the quality of water. We are destroying most of our natural water resources, both surface water and groundwater, and in many cases this is an irreversible process. Once the aquifer is contaminated, there is nothing more that we can do. Legislation is very important. I'm not a lawyer, but I will just mention in one slide an example for our solution to legislation. Education is very important, and it should start from kindergarten. Some people here ask about education. I believe that education is the key for everything, including the water scarcity. And of course, research and technology. I'm coming from the academia. They are very important. And to optimize the use of natural resources, we have to do a lot of research and technology things. So this is an example for the state of Israel. What we did to cope with the climate gradient. In Israel, it's the opposite. The south is very dry and the north is relatively wet. Not as rainy as here, but way more than the south. And in the mid-60s, it was the largest project almost in the world for a very small country. They built the national water carrier that connect the only freshwater lake in the Middle East all the way down to the southern part of the Negev desert. So basically, I live here in the desert, and when I'm taking a shower, I have no clue where the water is coming from, because there is a long pipe that connects all the water resources from the lake, from the 3 different aquifers, and from desalination plant. And the system decides what water to use according to the price of the energy and the situation of the resources at any given moment. So one day I can take a shower that is mostly desalinated water, and the other day it can be mostly water from the coastal aquifer. Okay, this is an example. Now, legislation. In Israel, all the water is the property of the state, and a landowner does not own the water under his property. There is one government agency, the Water Commissioner, that is in charge of all the water issues, quality, quantity, surface water, water for agriculture. It's all managed under one unit, and it's very, very centralized system. And it's very efficient, okay? It's very efficient because this unit knows everything about the water in the state, everything, and they need to sign and approve every movement, every new well, every new pipe must be approved by this agency. Now, I have to say that this legislation is very useful for a small country, which is young, small, and all the water actually is transboundary water that cross borders, but it's not necessarily the best for all the countries. I will just give an example from India. A few months ago, I was in a conference in India. The numbers are crazy. They have like more than 30 million registered wells, and they estimate that the same number of unregistered, and more than 2 million springs that are used for water registered. So obviously, controlling such a huge country with so many water resources is way more complicated, and it cannot always be completely centralized. Education, I will just bring one slide. This top model borrowed her face to give an example for the result of drought, and it is very efficient. I'm just going to say that in Israel, after a few years of drought, they started very massive advertisement, and they managed to save more than 15% of the annual water consumption just by very aggressive advertisement to the situation. So education is also very, very important. Now let's talk about the water balance. The deal is very simple. We want to minimize the output and maximize the input. Of course, that's easy. What it means minimizing evapotranspiration. You know that most of the water loss is to the atmosphere. Water is becoming vapor. We want to minimize that. We want to capture all the flood water. You know, most of the flood water goes eventually either to the ocean or to terminal lakes, which are typically saline, and we can save this water and use it. And of course, last but not least, as I mentioned, appropriate agriculture. So how can we do that? This is an example for an agricultural village in the southern part of Israel, a very dry area, as you can see. And all these greenhouses, this village is 100% based on agriculture in a very, very dry area. It's about 50 millimeters or 40 or 50 millimeters of rain per year. So how do they do that? The answer is very, very smart agriculture. Everything is in greenhouses. All the application of water is by subsurface drip irrigation, very efficient, minimizing evapotranspiration, irrigating only late at night, and so on and so forth. I'm not going to get into the details, but I will just give one example, and the example is of drip irrigation that was developed in Israel in the mid-60s. And the drip irrigation enable us to use the water in a very efficient way. The estimation is around 90% efficiency. And it's worth mentioning that this is a great business as well. You know, this is a method that was developed originally in the mid-60s. And since then, it was developed and developed. There are more than 500 patents only about drip irrigation, and 4 huge companies that each one worth more than a couple of $1 billion now, only from drip irrigation. So with the right technology, we can make good business, not only save water. And this is a classical win-win situation, okay? So the bottom line is that we really need to remember these 2 short sentences: more crop per land unit and more crop for drop. And if we work according to these 2 sentences all the way, we can do a lot of good things. This is an example for reservoirs to capture water, and one of the reservoirs is even fully covered to prevent evaporation. Because in this area, which is the Arava Valley, we have about 2.6 meter per year evaporation. So if you cover the reservoir, you save a lot of water as well. Now, this slide is very important because what it shows is the per capita consumption of water in Israel from the late 50s till nowadays. And we can see that with the appropriate water management, and there are no miracles, it's just appropriate water management, the country managed to reduce the consumption to less than 50% than what it was in the early 60s. So we can see that water use efficiency can be done and can significantly improve the overall water consumption. So it's not just talk about science. This is something that works practically. Now let's talk about production of new water, and I divided production of new water to the reuse of treated wastewater and desalination. Reuse of wastewater, and I'm referring to domestic wastewater, wastewater that we are producing. It means that we're taking the water and treating them, and nowadays we can treat them to really high quality, I will show that, and reuse it. So every drop of water is not being used once, it's being used again and again and again. But still the numbers are not that great. And this is funny because this slide I used about a couple of years ago, and when I prepared this lecture, I went to the web and checked the numbers, and I saw that the numbers in just 2 years are different because this is a very active area and more water is being reused. So in just 2 or 3 years in Israel, it changed from 80 to 86%. There is some increase in Spain as well. In the other countries I couldn't find, it's still very low. So we can use a lot of wastewater for whatever reason, and I'm not going to elaborate on it. There are explanations. In most other countries, this idea is not being used yet. The bottom line of using treated wastewater is, can be seen in this graph. We started to use treated wastewater from the mid-90s. Till the mid-90s, all the water that was used for agriculture was potable water, and since then you see less and less potable water and more treated wastewater, okay? So this is a real game changer in terms of water use efficiency. Now, we must remember that when we are using technologies like using treated wastewater, research is essential because we can make damage. It's not obvious that we can do whatever we want, play with Mother Nature, and everything will be perfect. And we need to make sure that we're not creating either short-term or long-term damage to our soils, to our groundwater, and of course to the crops. And indeed, there is a lot of ongoing research, and the research go on for 20, 30 years to make sure that we're not making damage, because this is very important. We do not want to create any damage. I will give one example for wastewater treatment in Israel. This is the largest wastewater treatment facility. It's called the Shafdan. It treats about 140 million cubic meter per year. All the water of the Tel Aviv metropolitan, all the big cities, about 2-point-something million people. All the wastewater goes here. There is the activated sludge stage. This is the first stage that all the wastewater treatment are based on. And then, interestingly, the water goes to infiltration lagoons. You can see it here, for example, and it infiltrates through very thick, unsaturated zone, dunes along the coast, and then it goes within the aquifer to ring of production wells and to agriculture. This is a very efficient process. I will show in a second, but we do have a big problem, and the problem is that these lagoons need a lot of space. And I'm talking about a very small country. And this is in the central part of Israel, so it's very, very expensive land. So there is no more land available, and there is more and more effluent, more and more wastewater. So we need to increase the efficiency of this process so we can infiltrate more water, but without changing the level of purification, okay? And I will skip this one. I will just show how efficient is the process. So this is the some parameters from the original wastewater, and then it goes to through the activated sludge, goes to these levels, and this is what we pumped eventually after the water infiltrates through this huge natural filter. And it is going on for more than 20 years successfully. So it's really, really high quality water. Actually, the quality of the treated water after this tertiary treatment is drinkable water, potable water. We are not drinking it due to regulations, but if we drink it, nothing will happen. Of course, that coming from the academia, I had to say that there is a lot of research involved. We're making a lot of research to improve the efficiency and with the same level of purification. We are mixing hydrogeophysics, hydrochemistry, and so on and so forth. Now let's talk a little bit about desalination, and this is an old cover page of a Time magazine for, I think, something like 15 years ago. You don't have to be a fish to drink seawater, which is what desalination is about. And in Israel, let's say that if you wanted to drink seawater until 2004, you had to be a fish. And now, we're desalinating more than 600 million cubic meter per year, which is about 75% from the overall consumption of potable water in Israel. So this was a huge game changer, because one of the advantages of desalination is that it's completely disconnected from the climate change, okay? So if it's a drought, doesn't matter. We're taking seawater and we are desalinating them, and we have enough water. Of course, it's all connected to the national water carrier that I mentioned earlier, so we get it directly into the system. Now, desalination went through a lot of progress and innovation. This is the first desalination experimental station in 1966, and this is how desalination plants look nowadays, more or less. Each one looks slightly different. And there is a lot of innovation, a lot of work that is being done. I will mention a few type of activities that we're doing in my institute on the different topics I mentioned, because after all, we're talking about science. So for example, we are looking into the impact of desalination on the marine environment. This is one of the major concerns, because we are pumping a lot of water from the ocean and discharging a lot of saline solution, much more saline than the seawater. So there is a concern what will happen to the marine environment, and there is a lot of research going on. So far, we don't see any impact in the last 15 years. We are looking into a process that is the major problem in desalination. We call it biofouling. It's microorganisms that build layers on the membrane and block it. So we are building membranes or developing membranes with less biofouling. We are trying to control the surface properties using new nanomaterials and 3D printers. And recently we managed to develop material that is antivirus, and viruses cannot grow on the membranes. And this is just an example. Let's talk about examples from energy-related research. So we are developing method for biowaste stabilization and reuse, solar hydrothermal reactors that is converting sludge into energy. We call it hydrochar. Very efficient, very interesting process that can be used, by the way, also in remote villages off-grid. Intensive recirculation of aquaculture with recovery of energy from biogas. Again, very interesting line of research that put the fish farms in a different perspective. In terms of hydrology, a few examples. We developed Vero zone monitoring system that enable us to look into contaminants before they reach the aquifer. And it's very successful. It's already bought by a company and installed in almost, I think, 90-something sites from Australia, New Zealand, the US, Europe, everywhere. Developed a system for spatial and temporal distribution of salts and contaminant in aquifer. We're working in a climate control laboratories to look into the real impact of climate change on the hydrological cycle. It's very interesting because everybody talks about climate change. The atmosphere will be 1 degree higher, but most of the people do not really check what's going to be the impact and is it important if this 1 degree will be during the day or during the night. It's a completely different ball game. Okay, that's one example. And we're using different technologies to look on the micro scale of processes like CT or MRI, which is connected to your work, magnetic resonance image, those that ask about what can we do with magnets, and so on and so forth. So I will try to summarize what can we do or how can we help, because most of this presentation was showing pretty negative things. So first of all, we need to remember that there are no miracles. And it doesn't matter how smart you are and how much money you have. No one can solve this food, water, sanitation problems like that. It's really complicated. Now, I divided it to what we should do in the developed countries and in the developing countries. In the developed countries, improvement of management and decision support systems is the major thing. In many cases, the problem in the developed countries is mostly politics. It's not technology. But if we improve the management and the decision support systems and adopt the right technologies and select the appropriate research topics, we can do quite well. In the developing countries, which is where the problems are the worst, we have a big problem. There is a lot that needs to be done. We need to first gain the basic information about the problems. In many cases that we're working, for example, in Africa, they know nothing about the local groundwater. They don't even know if there is aquifer below their village. So basic knowledge is really essential. And we should learn how to implement low-tech, robust technologies and a lot of education. So I think that if I'm trying to summarize what I was very briefly said, I think that you will agree that water is very precious resource and a very scarce commodity. And on the other hand, it's a very unstable resource. And awareness, education, innovation, and technology are really important and can make things much better. The food-water crisis is something that we cannot completely prevent given the population growth, the climate change, the desertification, and the lifestyle. We can't prevent it. But we can do a lot to make it better. And if all the parameters in the equation, the industry, the farmers, the decision makers, and the experts that do science will work together, we can do a lot to improve the situation. Research that in many cases is being considered as a luxury is really essential. Because if we do mistakes, sometimes the mistakes are irreversible. And if we can change them, it usually costs billions of dollars. And unfortunately, there are a lot of examples for that. So we cannot assume that a method that worked in one place, we can take it as is and adapt it in a different place. Because it's different climate, different hydrogeology, and so on and so forth. So we have to explore and make the right research. And I think that overall, if we do the right things, we can significantly improve the global food-water crisis. And I think that this is, at least from my end, the take-home message that I wanted you to get from this presentation. And I thank you. That's it.